So we're going to start a topic on optimization, which is the idea of having a function and being able to find minimum and maximum values just given the function. So what this lets us do is kind of circumvent making the graph in any way and just algebraically using calculus, where are these minimum and maximum values? And we'll look at relative minimums and maximums and absolute minimums and maximums. So where we're going to start is with the first derivative test and how we can use this to find the values, and then we'll go to looking at the second derivative test and how it can help us find the same values. And with that, we're going to be looking at relative minima and maxima first. So as a refresher of what it means to have a relative minimum or relative maximum, this is happening in a shorter window. And what I mean by that is, like, if I have this graph down here, and actually even if let's go ahead and put arrows at the end there. So in terms of absolute minimum, absolute maximum for this graph, there actually isn't any, because that's going to go off to negative infinity, that's going to go off to positive infinity. So in terms of y values, we can have absolutely anything for y, so there's no total maximum, total minimum that's happening. But when we talk about relative minimums and maximums, what we're doing is thinking kind of more zoomed in. So like if I go right here and just focus on this spot, then what I can do is I can see we're increasing, we're increasing, we're increasing, and then we hit this point right here, and then we start decreasing. So this right here would be called a relative maximum. It's increasing up to this maximum value, and then it starts decreasing away. And then what we can see is down here, this similar idea of decreasing down and down and down and down, and then we turn and start going up and up and up and up. And this behavior gives us a relative minimum. And then we're increasing, we flatten out a little bit, then start increasing again, and then we hit this relative maximum right here. So we can have more than one relative max or min, and they can be happening at different spots, but it's more about this zoomed in behavior. And then here's another relative minimum. So as we're seeing this change from increasing to decreasing, which if you imagine the slopes of the tangent lines, if we're thinking about our first derivative here, is that we have something positive, positive, and then starts flattening. In fact, our tangent line right at these spots are giving us a tangent line that's horizontal. So if I imagine my tangent line at each of these spots, we're seeing these critical values where our derivative is equal to 0 at each of those spots. Now with this graph, I love this graph because there's one extra spot that's actually occurring at, which is right here. This is a spot that also has a derivative of 0, and that's important to know, but with the behavior around it, and the idea that it's not changing, it goes increasing and then it keeps increasing, that behavior tells us that it's not actually a relative minimum or maximum. So all of those pieces I just described are written out in words up here. So relative minimum, this is where we're decreasing to the left and then increasing to the right. So if you think of each of these points as this value C, for relative minimum, we're decreasing, then increasing. Decreasing, then increasing. So what's going to happen is if we evaluate the derivative, it's going to change from a negative derivative to a positive derivative. So we have these negative slopes of tangent lines, and then it switches to positive slopes of tangent lines. Relative maximum, it would be increasing on the left-hand side and then decreasing on the right-hand side, which means we have positive derivatives, and then it switches to negative derivatives. And then this value could be neither a relative maximum or minimum at that value if it's the same sign on either side. So we have these positive slopes here, and then it's still positive slopes. So this is a spot where there's a critical value that's going to be showing up there because that's where derivative is equal to 0. But because it's the same sign, since it's positive on both sides, it's not actually a relative maximum or minimum. All right, so let's try this out. So we're going to go through using this first derivative test. So first thing we're going to do is find our critical values. And we also want to include points of discontinuity with these. We want to evaluate those as well. So we'll include those when we can. All right, critical values. So first thing I want to do is take the derivative of this. I'm just going to rewrite this function a little bit. Just to make it a little easier for me, I'm going to write it as 1/4 times x cubed, just to kind of separate that numerical coefficient. All right, taking the derivative, we'll have 3 times a fourth times x, 3 minus 1 minus 3. And what we want to do is to find our critical values. We're going to see where is this equal to 0. I'm going to add 3 to both sides. To get rid of that 3/4, I'm going to multiply both sides by 4/3. So those 3's actually nicely cancel. So we're getting x squared equals 4. And then I'm just going to take the square root of both sides. And when we do that, it's so important, we have our plus or minus. And square root of 4 is 2. So we end up with 2 critical values here, +2 and -2. So that was our first step. Then what we're going to do is what we did with our first derivative test, and we're going to set up our intervals. So in terms of intervals, and what can sometimes help here is to just quickly sketch a little number line. So like if I do -3, -2, -1, 0, 1, 2, 3, we're going to have these spots. At -2 is going to be a cutoff, and +2 is going to be a cutoff. So we're going to end up with 3 intervals. We're going to have everything less than -2, everything between -2 and +2, and then everything above. So there's my 3 intervals. So -infinity to -2, and -2 to +2, and 2 to +infinity. All right, so there are my test intervals. And what we're going to do is choose a value in each of these intervals to test. So my next step, I'm going to have some test values. And we're just choosing values that are in that interval. So how about a -3, 0, and +3. And then what we're going to do is look at f prime of those values. So what we're going to do is our f prime of x is over here. And we're going to think about what happens when we plug in our values. And all we want to do is figure out if it's positive or negative. But let's go ahead and use a calculator here. Actually, a little spoiler of a graph. Okay, so we're going to do 3/4, and this can be nice with the Desmos calculator because we can set it up so we can just keep editing what our input is. So that is positive, and then when we plug in 0, we get a negative, and then when we plug in +3, it's positive again. So my outcomes here, positive, negative, positive. And that's all we don't need the numerical values. We just want to see, is the derivative positive or negative? Because that's going to tell us about increasing or decreasing. So we looked at the sign of f prime of x at each of those test values. And then what we can do is make this conclusion of if it's positive, it's increasing there. If it's negative, it's decreasing and increasing. All right, so we're evaluating the sign change next. So if we change from increasing to decreasing, that's what our graph is going to look like there. So what we're being left with is this maximum value. So at this x equals -2, we are seeing a relative maximum. Then over here, we're switching from decreasing to increasing. Oh, I'm not going to put an arrow at the end there, sorry. So in that spot, we're seeing this for our graph, which means we're seeing a relative minimum. So at x equals +2, we're seeing a relative minimum. So with each of these, we saw a change in behavior. So that means our relative minimum and maximum exists. If it stayed the same, like if this was decreasing and then still decreasing, that would be a case where it doesn't exist. But with these, we're seeing that trend, and having this little sketch instead of trying to just memorize the rules can be really helpful of just knowing increasing to decreasing, decreasing to increasing, and how those make a maximum value like a hilltop or a minimum value at the bottom of a dip. All right, so we have our x coordinates. Now we want our y coordinates. So we know we have a relative maximum and a relative minimum. Now, writing the coordinates should be coming from our original function. So we have our x coordinates, we have a -2 for the maximum, and for the minimum, we have +2. But then to get the y coordinates out, we're gonna need some algebra. So, or not even algebra, we just need to plug it in, and we can use the calculator to help out with that. So with this one, we're taking x cubed. So -2 cubed divided by 4, and then -3 times a -2. And that is +4. So that's our relative maximum. And then for relative minimum, we're doing the same thing, but with a +2. So I'm just gonna delete out those positives, and that's a -4. All right, so the process there with our steps, getting the critical values so that we know the cutoffs for our intervals. Specifically, these are going to be the x coordinates for our relative maximums and minimums. Then using first derivatives, we're going to evaluate so that we can see on what intervals are we increasing and decreasing, so we can evaluate how the trend changes, and that lets us know whether we have a maximum or minimum. And then from there, once we figure out max and min, we can write them out, and just getting that y coordinate comes from our original function. So here, evaluating positive and negative, we're using our derivative function, but getting the y coordinates at the end, we want to go back to our original function. So let's take a look at that graph just to double check this in Desmos. So I graphed this, and we can see we're increasing, and then it turns to decreasing, and then it turns to increasing, which is exactly the trend that we found in our table there. And there's this relative maximum at -2, +4, and relative minimum at 2, -4. Then we'll talk about absolute minimums and maximums later on, but in terms of absolute, there wouldn't be any with this case because it goes up to infinity in both directions.